All right, hi folks, this is Larry Messalino. I'm recording a short video here. This is from Module 8 in STAT412. And I wanted to go through a few different kinds of hypothesis testing here in Module 8, one of which is comparing two means in a hypothesis test. All right, you might remember we've already talked about hypothesis testing for one sample. Now we want to look at hypothesis testing for two samples. Now, let me show you an Excel calculator that I put together, and I'll share this with you in course announcements. And I wanted to just mention a few things here. So here is a Excel calculator for Module 8. Now, there's two scenarios that you can come across when you're working in the homework. You might be given summary data, or you might be given raw data. Let me give you an example. Let's say I take a sample of 10 men and 10 women, and I want to compare average salaries, mean salaries for these two groups. Well, maybe someone has already calculated for me that the sample mean for these 10 men, I'm going to call it X sub 1, the sample mean for the 10 men is $53,000. The sample mean for the 10 women is 48,000, let's say. And the standard deviation for the men is, just making up some numbers here, 8.2. The standard deviation for the women is 7.6. The sample size for the men was 10, and the sample size for the women was 10. So I'm calling this summary data because someone has already calculated the mean for me. Well, that's what this calculator is going to help you with. Okay, notice here it says summary data. And in some of these problems, you're going to notice that the problem is going to tell you to assume the variances are equal or assume the variances are not equal. All right, here's another scenario. What if they gave you the raw data? So for the men, they actually gave me 10 values of their salaries, like 51,000, 58,000, 53,000, 59,000. And for the women, they gave me 10 salaries, 49,000, 61,000, 54,000, etc. So if they actually give me the raw data, it turns out Excel has built-in routines for this. And if you go under data analysis in Excel, you'll see that Excel has these kinds of functions built in. So let me go through both kinds of examples for you. So if you're given summary data, we're going to be using this section up here. But if you're given raw data, I'm going to use the built-in routines that are already available in Excel under the data analysis menu. All right, so let's go to this first example here and take a look at what they're asking us about here. All right, so this one says, engineers at an automobile manufacturing company are trying to decide whether to purchase brand A or brand B tires. And let me move this over here a little bit. All right. And to help them arrive at a decision, they're going to run an experiment using 12 of each tire brand. And they run the tires until they wear out. Test the hypothesis that there's no difference between these two brands of tires. All right, I'd like to know, is there no difference or is there a difference? You know, maybe I find out that tire B is better, wears longer, lasts longer. Of course, I want to know that. So let me click on this link and see what the sample data looks like, because I want to know, are they giving me raw data or are they giving me summarized data? Well, if I notice here, this is summarized data. Right? Because for the 12 tires, they've already calculated the mean for me. It's not like they're giving me 12 numbers. All right. Now, the other thing to notice here is it says, assume the populations are normally distributed with equal variances. So this Excel calculator that I put together here is based on assuming there's equal variances. Let me show that to you one more time here. Move this over a little bit. And notice here it says when variances are assumed equal. All right, so we're going to use this calculator. So if you remember, you put data in the yellow cells and you get the answers out of the green cells. All right, so let me go ahead and enter in the data here for this example. All right, so let me come up here. The first box says, what is the hypothesized difference between the two means? Well, notice here, they're actually saying we're assuming there's no difference. So I'm going to make this first yellow box here be 0. I'll show you another example later where you do assume that there's a difference between the means, but for us, it's going to be 0. All right, let me enter now the sample 1 mean that's given to me in the table. So I'm just going to copy this data here. So for sample 1, they're telling me 38,400. Standard deviation 1 is 5,000. The sample size is 12. Let's go to sample size 2. The mean is 39,700. The standard deviation is 6,000. And the sample size is 12. All right. Well, let me go and get the test statistic. Move this over a little bit here. For us, it looks like our test statistic is negative 0.577. We'll round it to 2 decimal places, negative 0.58. By the way, the setup of the null and alternative. Remember, the claim was there's no difference. Well, no difference means not equal to 0. Okay. How about the p-value? Well, if you remember, when there is a not equals in the alternative like this, I have to come over to this row. It says here, if the alternative contains a not equal symbol. And for that, it looks like the p-value is 0.5701. For this problem, they're going to ask you for a range. And in this case, the category would be p-values between 0.4 and 0.6, right? Because 0.57 falls within that range. All right, well, I want to come to a decision now. Well, let me go back to that table that we actually used back in module 7. Here it is. I'm going to move it down here to make it a little easier for us. And so what you do is you compare the p-value with alpha. All right, our p-value is 0.570. Now, in this case, they're not giving me a value of alpha, but when they don't give me a value of alpha, I use 0.05 as a kind of a default value. But our p-value is way bigger, right? 0.57 is way bigger than 0.05. Well, here it is. If the p-value is greater than alpha, then you fail to reject the null. So our answer is going to be do not reject the null. And if you notice these statements down here about failing to reject, we always say there's not enough evidence. So we're going to say insufficient evidence. Okay, folks, so if you have summary data, this calculator will help you with the test statistic and the p-value. All right, let me do another example like this. Let me go get another example. Let's see if number 4 is like this. All right, so this is talking about plasma exorbic acid levels of pregnant women for smokers versus non-smokers. And let's open up this data and see what they have here. So it looks like they have values of this acid value for non-smokers and smokers. Now, if you notice, this is raw data. I don't have summary data. So this is raw data. So I'm going to copy this data into Excel. And actually, I'm going to open up a blank Excel spreadsheet here. That'll make it easiest, I think. Let me open up a blank Excel spreadsheet. All right. And I'm just going to copy this data into Excel. So let me copy it. Just copy it to the clipboard. And then I'll paste it here. All right. So here's the data we got. All right. So let me come back and read the problem a little carefully. It says, is there evidence to conclude that there is a difference between levels of this acid for smokers and non-smokers? Assume the two data sets came from normal populations with unequal variances. It's important that I notice that this problem says unequal variances. All right, well, I want to go ahead and let Excel help me out here. I'm going to go up to the Data tab, and I'm going to go to Data Analysis. And this is going to be a t-test for two means where there's unequal variances. So you really have to make note of this condition that they're giving you, this assumption that there's unequal variances. All right, so let me go to Excel, and I'm going to come up here to the Data tab, and I'm going to come here to Data Analysis. And if you notice on this Data Analysis menu, here is a t-test assuming equal variances. Here's a t-test assuming unequal variances. So this is why you have to read the problem carefully to know which one of these routines you want, which one of these programs you want to use. For us, the problem said unequal variances. So I'm going to go ahead to this unequal variances. All right, let me clear this off the screen here. All right, so I'm going to select unequal variances. All right, when I do that, let me get the dialog box here. All right, so here's the dialog box that pops up. Now, what you have to do is tell Excel where the first column of data is. That's what they mean when they say variable one range. And then you have to tell Excel where the second column of data is. Well, the easiest way to do that is click your mouse over here on this little arrow here. I click it, and now I can use my mouse to select this column of data. Okay, and then let me go back. I think that I didn't select the second column, so let me undo that. Bear with me 1 second. Let me go back here to sheet 1. I'm going to do it over again, assuming unequal variances. All right, so now let me come here to select variable 2, and it's going to be this data. Okay, and I think that's it. And I'm going to put this in a new work. No, I'm just, you know what I'm going to do? I'm going to put it here in this spreadsheet right here. So I'm just going to click my mouse and say, put the data there. And here's the results. Let's take a look. All right, what I'm looking for here is the test statistic. Well, here is the test statistic for us, negative 0.16. They said round to 2 decimal places. So there's the test statistic. And now we want to find the p-value. Well, for us, our alternative had a not equal symbol. When you have a not equal symbol like this, we call this two-tail. Let me make a note of this. If the alternative has a less than, or if the alternative has a greater than, we call this a one-tail test. But if the alternative has a not equal symbol, like in our example, we call this a two-tail test. All right, so what that means for us is we want to come over here and grab this p-value right here for 2 tail test, which is 0.874. All right, but I know that if the p-value is greater than alpha, like it is here, then we fail to reject the null. I'm going to go back to that. Let me go back to this table that we can use here. Our p-value is greater than alpha, right? Our p-value is 0.874. That's greater than 0.05 that we assume for alpha, so we're failing to reject the null hypothesis. Let me scroll down here. So do not reject. There's not enough evidence here to conclude that there's a difference between this acid level for smokers and non-smokers. All right, let me do a couple more examples quickly here. Let's take a look at this one. This says study was conducted at Virginia Tech. Is there a density? Is there a difference in the density of organisms at two different stations on a stream? Okay. By the way, notice here they're telling us use alpha equal 0.05. Are the densities equal? And notice here it says assume observations are coming from normal populations with different variances. That means unequal variances. So I'm going to use the same Excel setup we did a few minutes ago. All right, so let me go back. Let's open up the data set. And I'm going to go ahead and copy this data into Excel. I'll make up a new sheet here. So let me copy this data into Excel. Here it is. Okay. And I know it's unequal variances. So I'm going to go back to data analysis. I'm going to use the same t-test to sample with unequal variances. Say, okay. The first column is going to be this data right here. The second column is going to be this data right there. And again, I'm just going to put the output here starting at D2. Say, okay. All right, well, here's the test statistic. Let me come here to the test statistic. 2.42. There it is. And again, notice because the alternative has a not equals, this is a two-tailed test we call it. So if it's two-tailed, this is the p-value to get 0.026. All right, well, let's do our comparison. In this example, the p-value is 0.026. Alpha, they told us in this problem, remember alpha is the same as level of significance. They told us to use 0.05. But in this example, the p-value is actually less than alpha. Well, the rule is if the p-value is less than alpha, then you should reject the null hypothesis. So reject the null hypothesis. And if I go back to that table here, if you notice when you reject the null hypothesis, we say there is enough evidence. So there is sufficient evidence. All right. So again, it's nice that Excel has a built-in routine to handle this. Let's go to number 6. Let's look at a few more. All right, let's do number 6 because this is different. This is a different type of test. So let's read about this one. It says a random sample of 88 adults is classified according to gender and number of hours of TV they watch. Use 0.01 level of significance, that means alpha, and test the hypothesis that the time spent watching television is independent of whether the viewer is male or female. Well, we call this a test for independence. Sometimes we call this a contingency table test. contingency table test. Because the way the data is set up, it's in a format called a contingency table. Notice here it says, click the icon to view the contingency table. So let me open that up so we can see what this table looks like. All right, so here's what they're showing me. Across the top, the columns say male, female for gender, and the rows say either over 25 or under 25 hours. So what I did is I counted how many males watch TV for over 24 hours. It looks like there were 14 males. I counted up how many males in the sample watch TV for under 25 hours. That was 26 males, and so on. So what I want to know is there a relationship between these two quantities? Number of hours you watch TV versus gender, or is there really no dependency? You know, males and females, watch TV at about the same rate. There's no dependence. Well, it turns out there's a setup for this, and I created a calculator for this. Let me go to that. So on this module 8 calculator, I created two tabs here. One is called contingency table, and the other is called goodness of fit testing. I'll talk about goodness of fit testing maybe in a second video, but for right now, let's do contingency table analysis. So here's the way we're going to do it. If you notice in the yellow cells, you're going to basically copy this data. And then the green cells are going to give us our answer. So let me copy. I could type in the column here. Let me do that. I'm going to call this males, call this females. And then the rows was watching TV over 25 hours and under 25 hours. All right. And now I'm just going to copy the numbers into these yellow cells. 14, 26, 28, and 20. Now, when you set up a test like this, it turns out the null and alternative always stay the same, meaning the null and alternative never change. Here's what it says. For the null, we assume the two variables are independent of each other. For the alternative, we assume the two variables are dependent on each other. So notice when it comes time to setting up null and alternative here, for the null, you always use the word independent. For the alternative, you always use the word dependent, or the phrase not independent means the same thing. All right, well, they want the test statistic. In this case, it's using a distribution called chi-squared. So chi-square is the distribution being used for this analysis. And this is the Greek letter chi, and the exponent 2 here means squared. So chi-squared. Well, here's the test statistic right here, 4.76. And then here's the p-value in this green box, 0.02. So let's do our comparison. The p-value is 0.029. I got that from the green box. This problem said use alpha of 0.01. When they say level of significance, that's the same as alpha. All right, but 0.029 is a number greater than 0.01. Well, here's the rule. If the p-value is greater than alpha, your decision should be fail to reject. So we're going to say do not reject the null hypothesis. And when you say fail to reject, your conclusion is there's not enough evidence. So there's not sufficient evidence. Okay, folks, so this is called a contingency table. Sometimes we call it a test for independence. I'm going to add that in here because that's probably a good thing to add in. So it's a hypothesis test for independence of two quantities. All right, let me do another quick example like this. Let's see if there's another one like this. Let's take a look at this one. This one is asking you to fill in this green table here. So let me show you this example here. So it says, use the contingency table to calculate marginal frequencies and find the expected frequency for each cell. All right. Well, first, let me copy the data here. So it looks like we're analyzing whether athletes stretch or not stretched. And then we want to investigate whether they get injured or not injured. You know, this would tell me, does the rate of injury depend on stretching? Or maybe it doesn't depend on, maybe they're independent. If these two quantities are independent, it would say it doesn't matter if you stretch or don't stretch before a sports game, the rate of injury stays the same. There's no dependence. Or maybe we're going to find that there is a dependence. Maybe it does make sense to stretch before a game in order to reduce injuries. All right, well, let me type in the numbers here. 15, 208, 30, and 197. Okay. All right, now let me come here to, let me move this over a little bit. You know, this question is really not asking you to do a hypothesis test. This question is just asking you to fill in these numbers in these blue boxes. Well, for this first part, all they're asking you to do here is add these rows straight across. So if you take 15 plus 30, that's how they get 45. If you take 208 plus 197, that's how you get 405. They call you call these marginal frequencies. Just means add the rows straight across. Well, in addition to that, you can add the columns straight down. So I'm going to add these columns straight down also. 15 plus 208 gets me 223. 30 plus 197 gets me 227. And 45 plus 405 gets me 450. All right, so this first table is easy to fill in. All you have to do is add the rows straight across and add the columns straight down. Let me go down to this bottom one. It says, find the expected frequency. Well, these green boxes are doing it for you also. Notice 22.3 is in that green box. So that's 22.3 there. Here's 22.7. Well, here's 22.7. So these green boxes are giving you the expected data here. What this is what would be the expected number in each cell if we assumed the two quantities are independent? And there's a calculation for this that you can see in the textbook. But these green cells will work out the expected frequencies for you for this kind of a question. All right. Let's do this one. So this one, again, is asking us to analyze this kind of a contingency table. Okay. So it says here, the following table lists the results of an ability of dogs to use their sense of smell to detect malaria. So notice the columns are malaria present, not present. Dog was correct, dog was wrong. Now, you know, in this example, they're actually giving me a calculator output. So let me click here and see what this calculator output looks like. Well, it looks like they're actually giving me, they're actually giving me the test statistic and the p-value. This number right here is the test statistic. So for our example here, the test statistic, and we label that as a chi-squared value, is 19.489. Here's the p-value. It's labeled just as p. So the p-value is 1.0115 e to the negative 5. Well, e to the -5 is a shortcut for scientific notation. What it's telling you when you see e to the -5, it's telling you to take this decimal point and move it to the left 5 places. So really this p-value is going to be 0.00001 0115. So it's a shorthand way to say the p-value is a very, very small number. Essentially, the p-value is 0. Now, I could have typed these numbers into my Excel calculator to get the same results, or I could just use this calculator output. I'm going to type it here just to see if our calculator gives us the same results. I'm going to put 123 here, 52 here, 131. I'm just copying these numbers from my labs into the yellow boxes here. And notice we get the same test statistic and the same p-value. So the test statistic is 19.49. The p-value is 0. Well, definitely in this case, the p-value is less than alpha, right? Because the p-value is 0 here, and that's less than, we assume, 0.05. Well, if the p-value is less than alpha, we're going to reject the null hypothesis. So let me scroll down here to go to the choices. So we're going to reject the null hypothesis. And remember, the null hypothesis always makes a statement about independence. The alternative makes a statement about dependence, right? All right. Folks, I think there's some other examples here of what's called goodness of fit test. Let's see what this one is like. Oh, so this one is, let's do one more. This is a contingency table. So I'm just going to copy these numbers into the yellow boxes because it's a contingency table. So this is going to be 446,295, then a 559,928. Let me see here. The test statistic turned out to be an error message. So let me figure out what's causing that. All right, folks. Yeah, I figured out I had a small mistake in my Excel command, so I fixed it. So the test statistic here is 101.984. The p-value is 0. Well, when the p-value is 0, notice it says here use a 0.05 significance level. Well, in this example, definitely the p-value is less than alpha. We're rejecting the null hypothesis. Remember, the null hypothesis is that the variables are independent. So that means we can reject the claim that gender is independent of whether a call is overturned. But because we're rejecting the null, that's, we say, warrants rejection. And we had to make sure that this null hypothesis referenced independence here. All right, folks, hope this is helpful to get you started in the Module 8 homework. I'm going to record a second video because there's another topic here called goodness of fit testing, but I'll include that in a second video. All right, thanks, folks.